Anthony Raj. He has pursued his bachelor's, master's, and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Tiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to UGC lecture series BR Mathematics Semester 1 Lecture 6. In this lecture we are going to see three-dimensional analytical geometry. In three-dimensional analytical geometry, coplanar lines, shortest distance between skew lines, then summary are the concepts we are going to see in this lecture. Coplanar lines. We know two lines or more than two lines are said to be coplanar if these lines lie on the same plane. So, a set of lines that lie on the same plane is called coplanar lines. When the both lines are in symmetrical form, the equation of a plane containing the two lines will be different. When one line is symmetrical form and another one is in interceptal form, the equation will be different. And when both the lines are in general form, equation of a plane containing the line will be different. So, we are going to see all the three concepts in the coplanar lines. Let us take the first thing, when both the lines are in symmetrical form. To obtain the condition that both two lines may intersect, an equation of the plane in which they lie, what we are in need is, we are in need of the equation of two lines. Equation of the two lines are given by x minus alpha 1 by L1 is equal to y minus beta 1 by M1 is equal to z minus gamma 1 by N1. This is the equation of a line. Let us keep this as equation 1 and go to the equation of the second line, that is x minus alpha 2 by L2 is equal to y minus beta 2 by M2 is equal to z minus gamma 2 by N2. Keep this as equation 2. So, these two equations are the equations of two lines. Now, the equation of a plane through the line 1 is given by equation 3. Equation 3 is a into x minus alpha 1 plus b into y minus beta 1 plus c into z minus gamma 1 is equal to 0. So, this equation is the equation of a plane which passes through the line given by equation 1. Now, this a L1 plus b M1 plus c N1 is equal to 0. Keep this as equation 4. If line 2 passes in the same plane, then the normal of this plane is perpendicular to 2. First, we have seen line 1 passes through the plane, equation of that plane is given by this equation. Next, line 2, the line given by equation 2 lies in the same plane. For that, the normal of this plane should be perpendicular to equation 2. So, we have this AL2 plus BM2 plus CN2 is equal to 0. So, keep this as equation 5. Further, since the point alpha 2, beta 2, gamma 2 also lies on the plane, then A into alpha 2 minus alpha 1 plus B into beta 2 minus beta 1 plus C into gamma 2 minus gamma 1 is equal to 0. So, this is the condition when the point alpha 2, beta 2, gamma 2 lies on the plane. Keep this as equation 6. Now, we need to eliminate that ABC from equations 4, 5 and 6, where equation 4 is A L1 plus B M1 plus C N1 is equal to 0, and equation 5 is A L2 plus B M2 plus C N2 is equal to 0. Then equation 6 is A into alpha 2 minus alpha 1 plus B into beta 2 minus beta 1 plus C into gamma 2 minus gamma 1 is equal to 0. In all the three equations ABC exists. Eliminate that ABC, we will get the required condition. The required condition is in determinant form. The obtained determinant is alpha 2 minus alpha 1, beta 2 minus beta 1, beta 2 minus beta 1, and L1, M1, N1, then L2, M2, N2 is equal to 0. Now, eliminating the ABC from the three equations, we get the condition as alpha 2 minus alpha 1, beta 2 minus beta 1, and gamma 2 minus gamma 1, L1, M1, N1, L2, M2, N2 is equal to 0. So, this is the required condition for the two lines to be coplanar, and hence the required plane. So, in this explanation we are discussing the condition for the two lines to be coplanar and the equation of the plane in which that two line lies. This determinant is the equation of the plane that two line lies. That equation is x minus alpha 1 into y minus beta 1, L1 M1 N1, L2 M2 N2 is equal to 0. So, this is the equation of plane in which the two line exist. Then the next thing is when one line is in symmetrical form and the other in general form. To obtain that condition, the lines x minus alpha by L is equal to y minus beta by M is equal to z minus gamma by N. So, and x A1 plus y B1 plus z C1 is equal to 0, and x A2 plus y B2 plus z C2 is equal to 0 are coplanar. So, here we are going to learn this line are coplanar, and any point on the first line is given by x minus alpha by L is equal to y minus beta by M is equal to z minus gamma by N. So, any point on that first line is LR plus alpha and MR plus beta, NR plus gamma. So, this point will lie on the second line also. The second line is x A1 plus y B1 plus z C1 is equal to 0, and x A2 plus y B2 plus z Z2 is equal to 0. This is the second line. In this second line, this point also should lie. Then we get the condition A1 into LR plus alpha plus B1 into MR plus beta plus C1 into NR plus gamma plus D1 is equal to 0. This is the condition this is the condition for the point lie on both the lines. If we simplify this condition, we will get R is equal to minus into A1 alpha plus B1 beta plus C1 gamma plus D1 by A1L plus B1M plus C1N. Equating the values of R, we get the required condition as A1 alpha plus B1 beta plus C1 gamma plus D1 over A1L plus B1M plus C1N is equal to A2 alpha plus B2 beta plus C2 gamma plus D2 over A2L plus B2M plus C2N. So this is the required condition for the two lines to be coplanar. This condition is for when one line is symmetrical form and the other one is in general form. From this discussion, following remark arises, that is, in the above condition both the denominator should not be equal to 0. If both the denominator equal to 0, then 0 is equal to 0 is the condition we get, which is not acceptable. So in the above condition, both the denominators should not be equal to 0. The next case for the coplanar line is when both the lines are in general form. In the earlier two cases, we discussed when one line is in symmetrical form and the other one is general form, then when both the lines are in symmetrical form. These are the two cases we discussed. Now the third case is when both the lines are in general form. To obtain the condition for two lines to be coplanar when both the lines are in general form, the lines may intersect. The lines may intersect. When the lines intersect, we will get these equations as the equation of a line. We learnt in the earlier lectures that a line can be obtained from the intersection of two planes. Then we know the equation of a plane. Any first degree equation with x, y, z is an equation of a plane. Ax plus by plus cz plus d is equal to 0 is a first degree equation in x, y, z. This equation represents the equation of a plane. Then another plane will also have the same kind of equation. When these two planes intersects, we will get two equations. That two equations give the equation of a line. So here this xa1 plus yb1 plus zc1 plus d1 is equal to 0. xa2 plus yb2 plus zc2 plus d2 is equal to 0 gives the equation of one line. Then the equation of the second line is xa3 plus yb3 plus zc3 plus d3 is equal to 0, and xa4 plus yb4 plus zc4 plus d4 is equal to 0 is the equation of the second line. Now from these four equations, actually we should keep two equations as one equation because two equations represents a single line. So in these equations, eliminating x, y and z, we will get a determinant like this. This determinant value is the required condition for two lines to be coplanar. This condition is the condition when both the lines are in general form. So the condition is determinant of a1, b1, c1, d1, a2, b2, c2, d2, a3, b3, c3, d3 and a4, b4, c4, d4 is equal to 0 is the required condition. So from this discussion, we discussed the required condition for two lines to be coplanar. Now let us apply these concepts in the problem. Now see example 1. In this example, show that the lines x plus 3 by 2 is equal to y plus 5 by 3 is equal to z minus 7 by minus 3 and x plus 1 by 4 is equal to y plus 1 by 5 is equal to z plus 1 minus 1 are coplanar, and find the equation of the plane containing them. So in this problem we are going to apply the concepts which we learnt in the earlier discussion. Solution to this problem can be obtained like this. First, go to the given condition. The equation of the plane which contains the first line and parallel to the second is given by this determinant, that is x plus 3 y plus 5 z minus 7 2 3 minus 3 and 4 5 minus 1 is equal to 0. Determinant of this one is equal to 0 gives the equation of a plane which contains the first line and is parallel to the second one. In this example, we are going to show that the lines are coplanar and we are going to find the equation of the plane containing them. To that, first we get the equation of the plane which contains the first line and parallel to the second line. Now simplify this determinant. If we simplify that determinant, we will proceed like this: x plus 3 into minus 3 plus 15 minus y plus 5 into minus 2 plus 12 plus z minus 7 into 10 minus 12 is equal to 0. This is the expression we get after expanding that determinant. Simplify this equation. We will get x plus 3 into 12 minus y plus 5 into 10, because minus 2 plus 12 gives 10, plus z minus 7 into minus 2, 10 minus 12 minus 2 is equal to 0. Now, further simplification of this gives 12x plus 36, 12 into 3 36, minus 10y minus 50 minus 2z plus 14 is equal to 0. Now, 12x minus 10y minus 2z minus 50 plus 50 is equal to 0. This 50 and this 50 gets cancelled. So, the resultant equation is 12x minus 10y minus 2z is equal to 0. Further simplification of this gives 6x minus 5y minus z is equal to 0 is the equation of the plane which contains the line x plus 3 by 2 is equal to y plus 5 by 3 is equal to z minus 7 by minus 3, and parallel to the line x plus 1 by 4 is equal to y plus 1 by 5 is equal to z plus 1 minus 1. So, the obtained equation is the equation which contains this line and parallel to this line. That plane is 6x minus 5y minus z is equal to 0. As easily seen from the equation of the plane, this plane passes through the line minus 1 minus 1 minus 1. How it is obtained is, substitute this minus 1 here. So, minus 6, then plus 5, then plus 1. So, is equal to 0. So, this point satisfies this equation. So, this plane passes through this point on the second line. So, second line also contains the same one. So, second line also contains the second one. So, these two equations are these two lines are coplanar. These two lines are coplanar. This is how we can solve this problem. So in this problem we learnt that how to show that two lines are coplanar and find the equation of a plane containing them. So first we took the equation of a plane. This plane contains the first equation and parallel to the second one. Then we proceeded. Finally we got these two lines are coplanar. Next, shortest distance between skew lines. That's the next topic we are going to discuss. If two lines are parallel, if two lines are non-intersecting, then the shortest distance between the two lines can be obtained using the coordinate geometry. First, let us see the shortest distance between the lines can only have the meaning if the lines do not intersect or the lines are not lying in the same plane. So lines which have this character are called skew lines. Then the length between them is a perpendicular. Length between them is nothing but a perpendicular to both the skew lines, and that length is called the shortest distance between the lines. Shortest distance between the skew lines. This shortest distance can be obtained in different forms. As we have discussed earlier, to show two lines as coplanar, we took three different cases. When both the lines are in symmetrical form, when one line is in symmetrical form and other one is in non-symmetrical form, when both the lines are in general form. Like that, three different cases we discussed in the last discussion. Similarly, here also three different cases can be discussed. The shortest distance between the skew line is obtained when both the lines in symmetric form, when one line is in symmetrical form and the other one is in general form, when both the lines are in general form. Here we are going to take only the first case. The first case is when both the lines are in symmetrical form. Let us see, when both the lines are in symmetrical form, two ways are there to find the shortest distance between the lines. That two ways are projection method and the coordinates method. Projection method and the coordinates method. In projection method, a length of the shortest distance is given by L into alpha 1 minus alpha 2 plus m into beta 1 minus beta 2 plus n into gamma 1 minus gamma 2. So this is the length of the shortest distance between the two lines. Here this L, M, N are direction cosines of the shortest distance, and this alpha 1, beta 1, gamma 1 and alpha 2, beta 2, gamma 2 are the coordinates of the 2 points present or exist in the first and second line. So in projection method, this is the formula or equation used to calculate, to find the shortest distance between two lines. So let us apply that concept in this example. Here two lines are given. The first line is x minus 1 by 2 is equal to I minus 2 by 3 is equal to z minus 3 by 4. This is the equation of the first line, and the equation of the second line is x minus 2 by 3 is equal to y minus 4 by 4 is equal to z minus 5 by 5. Find the shortest distance between these two lines. Solution to this problem can be obtained first taking the directional cosines. Let L, M, N be the directional cosines of the given directional cosines of the shortest distance. then the shortest distance is perpendicular to both the lines. The shortest distance is perpendicular to both the lines. Therefore, we have 2L plus 3M plus 4N is equal to 0 as one equation, and 3L plus 4M plus 5N is equal to 0. That shortest distance is perpendicular to both the lines, so that we get these two equations. Keep the equation as 1 and equation 2. Then solving these two equations, we get, solving equations 1 and 2, we get L by 15 minus 16 is equal to M by 12 minus 10 is equal to N by 8 minus 9. Further simplification of this gives L by minus 1 is equal to M by 2 is equal to N by minus 1. Or further simplification of that gives L by 1 is equal to M by minus 2 is equal to N by 1. Therefore, we will get the value of L as 1 by root 6 and M as minus 2 by root 6 and N as 1 by root 6. These L, M, N are the directional cosines of the shortest distance. Then point P, which has coordinates 1, 2, 3, and point Q, which has coordinates 2, 4, 5, are the points on the given lines. Are the points on the given lines. So, the projection of PQ, projection of PQ on the shortest distance is given by SD shortest distance is equal to 2 minus 1 into 1 by root 6 plus 4 minus 2 into minus 2 by root 6 plus 5 minus 3 into 1 by root 6. Further simplification of this, we get the value as minus 1 by root 6. Let us take only the magnitude. So, the shortest distance between the two lines is given as 1 by root 6. This is the solution of the given problem. So, from this problem we learnt that how to find the shortest distance between two lines. So, from this lecture we learnt the condition for two lines to be coplanar, then the definition of coplanar lines. Coplanar lines are the lines which lies on the same plane. Then condition satisfied by the lines to be coplanar is obtained in three different forms. That is, when both the lines in symmetric form, and when one line is in symmetric form and the other in general form, when both the lines are in general form. Then we discussed the shortest distance between the skew line. The equation to get the shortest distance between two skew lines in projection method is given as L into alpha 1 minus alpha 2 plus M into beta 1 minus beta 2 plus N into gamma 1 minus gamma 2. So, this is the equation to get the shortest distance between the skew lines. These are all the concepts we discussed in this lecture. After listening to this lecture, you can answer the following questions. What is known as coplanar lines? prove that the lines x by 1 is equal to y minus 2 by 2 is equal to z plus 3 by 3 and x minus 2 by 2 is equal to y minus 6 by 3 is equal to z minus 3 by 4 are coplanar, then find the length and equations of shortest distance between the lines 3x minus 9y plus 5z is equal to 0, which is also equal to x plus y minus z, and 6x plus 8y plus 3z minus 13 is equal to 0 is equal to x plus 2y plus z minus 3. So, these questions can be answered after listening to this lecture. Thank you.